Welcome to Chapter 11 of the AEON-CASIMIR Dossier, where we move beyond the theoretical navigation and metric steering of previous chapters and dive into the physical reality of the AEON LCV Omega-1 craft. This chapter answers the fundamental question: what is the vehicle made of, and how does it survive the extreme physics it generates? We'll explore the unique philosophy behind its construction, the revolutionary materials used, and the ingenious geometry that allows the craft to exist in engineered space-time fields without succumbing to destructive forces. Let's begin our journey into the heart of advanced propulsion architecture. The objective of Chapter 11 is to define the physical architecture that enables the AEON LCV Omega-1 to operate safely within engineered space-time fields. Unlike conventional aerospace vehicles, which are designed to withstand and distribute physical forces, this craft is engineered so that those forces never fully couple to its structure. We'll see why traditional materials and designs fall short, and how the AEON-CASIMIR approach fundamentally rethinks what a vehicle must be to survive its own physics. This sets the stage for a new paradigm in advanced vehicle construction. Traditional aerospace materials are chosen for their ability to withstand stress, distribute loads, and resist failure under extreme conditions. However, in the AEON-CASIMIR framework, these conventional approaches are insufficient. The craft is not designed to resist forces in the classical sense. Instead, it is built so that those forces are isolated or redirected, never fully impacting the structure. This radical shift in design philosophy is essential for operating in the unique space-time domains engineered by the craft's propulsion systems. Geometry is not just about aesthetics in the AEON LCV Omega-1. The domed lenticular or disc-shaped geometry is chosen for its ability to generate symmetric curvature, contain toroidal fields, and maintain uniform Casimir boundary conditions. This shape ensures smooth geodesic flow over the craft, minimizing any discontinuities that could destabilize the protective slip layer. In essence, the geometry itself becomes an active component in the containment and management of the craft's engineered fields. Unlike traditional vehicles that rely on structural resistance, the AEON LCV Omega-1's hull functions as a multi-layer electromagnetic and vacuum boundary. Its primary roles are to define the limits of the Casimir cavity, anchor plasma field nodes, and provide electromagnetic phase control. Mechanical loads are intentionally minimized at the hull, shifting the focus from brute strength to precise field management. This approach allows the craft to operate in environments that would destroy conventional vehicles. The hull of the AEON LCV Omega-1 is a sophisticated, multi-layered structure, each layer serving a distinct field-related function. From the exterior inward, we find the slip layer interface region, a transitional space-time zone, the metamaterial boundary skin, which features anisotropic permittivity and negative index response, the structural lattice core designed for shape retention rather than load bearing, and the internal coherent frame shell, which maintains internal metric continuity. This layered approach ensures that every part of the hull actively contributes to field containment and stability. The outermost region of the hull is the slip layer interface, a transitional space-time zone that is not made of conventional material. This region acts as a buffer between the engineered fields and the external environment, ensuring that the intense physics generated by the craft do not directly interact with the hull's material layers. This slip layer is crucial for maintaining the integrity of the entire field containment system. Beneath the slip layer lies the metamaterial boundary skin. This advanced layer is engineered for anisotropic permittivity and features a negative index response that is frequency selective. These properties allow for precise control over electromagnetic boundaries, enabling the hull to manage field interactions with exceptional accuracy. The metamaterial skin is a key innovation in ensuring the craft's survivability in extreme environments. The structural lattice core is designed for high stiffness and low density. Unlike traditional cores, it is not intended to bear heavy loads. Instead, its primary function is to retain the craft's shape and provide a stable framework for the field containment layers. This core is an essential part of the hull's overall architecture, ensuring that the geometry remains precise, even as external conditions change. At the innermost layer, the internal coherent frame shell maintains internal metric continuity. This means that the internal environment of the craft remains stable and consistent, regardless of the external field dynamics. The frame shell anchors equipment and preserves alignment, ensuring that all systems operate within a protected and predictable reference frame. This is vital for both the safety of occupants and the performance of onboard systems. Materials for the AEON LCV, Omega-1, are chosen not just for their mechanical properties, but for their electromagnetic, quantum, and thermal behaviors. Candidate materials include nano-engineered metamaterials, layered graphene-like lattices, high-temperature ceramic composites, and superconducting or near-superconducting films. These advanced materials enable precise electromagnetic boundary control, low decoherence coupling, and rapid thermal redistribution, key factors for the craft's unique operational requirements. Nano-engineered metamaterials are at the forefront of the AEON LCV, Omega-1's hull design. These materials are custom-built at the nanoscale to exhibit properties not found in nature, such as negative refractive index and tunable electromagnetic responses. Their unique structure allows for unprecedented control over field interactions, making them essential for the craft's field containment and survivability. Layered graphene-like lattices provide exceptional strength, flexibility, and thermal conductivity. These lattices are engineered to support the hull's structural integrity while enabling rapid redistribution of heat and electromagnetic energy. Their layered nature also contributes to the overall field containment strategy, ensuring that the hull remains stable under a wide range of operational conditions. High-temperature ceramic composites are used in the hull to withstand the thermal extremes encountered during advanced propulsion operations. These materials maintain their structural and electromagnetic properties even at elevated temperatures, ensuring that the hull's performance remains consistent regardless of external conditions. Their inclusion is vital for the craft's ability to operate in high-energy environments. Superconducting or near-superconducting films are integrated into the hull to enable rapid electromagnetic boundary control and minimize decoherence. These films allow for the efficient management of energy and field interactions, which is essential for maintaining the stability of the craft's engineered spacetime domains. Their use represents a significant advancement over traditional conductive materials. The core principle behind the AEON LCV, Omega-1's hull, is field containment rather than structural resistance. The hull is designed so that the divergence of the field vector approaches zero at its boundary, effectively preventing field leakage, structural loading, and thermal hotspots. This containment strategy is what allows the craft to operate safely within its own engineered spacetime fields. Inside the protected spacetime domain created by the hull, classical mechanical loads are suppressed. The craft does not experience the same stresses and strains as conventional vehicles. Instead, the hull's design ensures that forces are decoupled from the structure, allowing for safe operation even in extreme field environments. This suppression of classical loads is a defining feature of the AEON-CASIMIR approach. The internal structural frame of the AEON LCV Omega-1 is not designed to carry propulsion or gravity loads. Instead, its primary functions are to maintain the craft's geometry, anchor equipment, and preserve alignment. Occupants and onboard systems remain within a free-fall reference frame at all times, further reducing the impact of external forces on the internal environment. Heat management in the AEON LCV Omega-1 is achieved through electromagnetic redistribution, plasma absorption, and radiative phase cycling. Because drag and friction are suppressed by the engineered fields, the hull experiences far less heating than conventional vehicles, even during high-speed operations. This advanced thermal management ensures the craft's systems remain within safe operating temperatures at all times. One of the remarkable features of the AEON LCV, Omega-1, is that it does not experience classical re-entry heating. The suppression of drag and friction by the craft's fields means that the rate of heat transfer to the hull is much lower than in conventional vehicles. This allows for safer and more efficient operation during atmospheric transitions and high-speed maneuvers. If the craft's field systems degrade, classical loads gradually re-enter the structure. The hull is designed to tolerate temporary Newtonian operation, experiencing increasing classical stress as the fields weaken. Automatic decoherence and metric relaxation mechanisms are in place to protect the craft during such events, ensuring that it can survive until field integrity is restored or a safe shutdown is achieved. The hull of the AEON LCV Omega-1 can be made transparent or opaque to electromagnetic waves at selected frequencies. This tunable transparency allows for the integration of embedded sensors, external field measurement, and passive observational capabilities. The ability to actively control hull transparency is a significant advantage for both navigation and scientific observation. With its tunable electromagnetic properties, the hull can host a variety of embedded sensors. These sensors enable real-time monitoring of external fields, environmental conditions, and craft performance. The integration of sensors directly into the hull structure enhances the craft's situational awareness and operational safety. Protection from radiation and high-energy particles is achieved through a combination of slip layer deflection, metric redirection, and plasma interaction. High-energy particles are guided along altered geodesics, effectively bypassing the interior volume of the craft. This advanced shielding strategy ensures the safety of occupants and sensitive equipment, even in the most hostile environments. Let's visualize the hull's layered structure with a technical cutaway. From the exterior slip layer to the metamaterial skin, through the structural lattice core, and finally to the internal frame shell, each layer is engineered for a specific field function. This cutaway reveals the complexity and precision of the AEON LCV, Omega-1's construction, highlighting how every component contributes to overall field containment and survivability. The AEON LCV Omega-1 is assembled from modular, field-aligned segments. Each segment is precisely manufactured and aligned to ensure phase coherence across the entire hull. The use of layered metamaterial shells and precision geometry nodes allows for rapid assembly and maintenance, while maintaining the stringent tolerances required for field containment. Manufacturing tolerances for the AEON LCV Omega-1 are driven by the need for precise phase alignment, not just mechanical fit. This means that every component must be manufactured and assembled with extreme accuracy to ensure that the hull's field containment properties are maintained. This level of precision is essential for the craft's operational safety and performance. The geometry of the hull directly influences the craft's navigation and control systems. The domed lenticular shape enhances metric steering efficiency, coherent stability, and energy containment. The hull's shape is not just a passive structure, but an active participant in the craft's control architecture, affecting how it moves and responds to its environment. The hull's geometry and material properties are tightly integrated with the craft's navigation and control systems. This integration ensures that changes in field configuration or operational mode are matched by corresponding adjustments in the hull's electromagnetic and structural responses. Such synergy is crucial for maintaining stability and performance during dynamic maneuvers. Field isolation is a core concept in the AEON-CASIMIR approach. By decoupling the craft's structure from external forces through engineered fields, the hull is protected from the extreme physics generated during propulsion. This isolation is achieved through a combination of geometry, material selection, and precise field management. Metric decoupling refers to the process of separating the craft's internal space-time metric from external influences. This allows the AEON LCV Omega-1 to maintain a stable internal environment, even as it manipulates spacetime for propulsion and navigation. Metric decoupling is essential for both the safety of occupants and the integrity of onboard systems. Stress energy redirection is the process by which the hull's design channels and redistributes energy away from the structure, rather than absorbing it. This is accomplished through the use of advanced materials and field configurations, ensuring that the craft remains unaffected by the intense forces generated during operation. Uniform Casimir boundary conditions are maintained by the hull's geometry and material composition. These conditions are critical for stabilizing the engineered fields that enable advanced propulsion. The hull's design ensures that Casimir effects are harnessed rather than becoming a source of instability. The domed lenticular geometry of the hull is optimized for toroidal field containment. This configuration allows for the creation of stable, self-contained field structures that protect the craft from external influences. Toroidal containment is a key factor in the AEON LCV, Omega-1's ability to operate in engineered spacetime domains. The hull serves as an anchor for plasma field nodes, providing stable points for field generation and control. This anchoring is essential for maintaining the integrity of the craft's protective fields and ensuring consistent performance during dynamic operations. Electromagnetic phase control is achieved through the metamaterial boundary skin and other advanced materials in the hull. This control allows for precise manipulation of field interactions, which is critical for both propulsion and protection. The ability to manage electromagnetic phases is a hallmark of the AEON-CASIMIR design philosophy. Low decoherence coupling is a critical property of the hull's materials, ensuring that quantum effects remain stable and predictable. This property is essential for maintaining the integrity of the craft's engineered fields and for supporting advanced propulsion technologies. Rapid thermal redistribution is enabled by the hull's advanced materials, such as layered graphene-like lattices and high-temperature ceramics. This capability ensures that heat generated during operation is quickly spread throughout the structure, preventing hotspots and maintaining overall stability. The domed profile of the hull ensures uniform geodesic flow over the craft, minimizing curvature discontinuities that could destabilize the slip layer. This uniformity is essential for maintaining the stability of the protective fields and for ensuring smooth operation during high-speed maneuvers. The internal coherent frameshell not only maintains metric continuity, but also provides secure anchoring points for equipment and preserves precise alignment. This ensures that all onboard systems remain properly oriented and functional, regardless of external conditions or maneuvers. Occupants and systems inside the AEON LCV, Omega-1 remain within a free-fall reference frame at all times. This means that, regardless of the craft's acceleration or maneuvering, the internal environment remains stable and comfortable, with minimal sensation of external forces. In the event of field system degradation, automatic decoherence and metric relaxation mechanisms activate to protect the structure. These systems allow the hull to tolerate temporary increases in classical stress, ensuring survivability until normal field operations can be restored. The hull's transparency to electromagnetic waves is not fixed, but can be actively tuned. This allows for dynamic adaptation to different operational needs, such as sensor integration, communication, or stealth. Active transparency tuning is a powerful tool for mission flexibility. Phase alignment is the guiding principle in the manufacturing and assembly of the AEON LCV, Omega-1. Every segment and layer must be precisely aligned to maintain the integrity of the craft's field containment properties. This requirement drives the need for advanced manufacturing techniques and rigorous quality control. In summary, Chapter 11 establishes that the AEON LCV, Omega-1, is not built to resist forces in the traditional sense. Instead, geometry, advanced materials, and field containment strategies work together to isolate the craft from extreme physics. Structural survivability comes from decoupling and precise field management, not brute armor. This revolutionary approach sets the stage for the next chapter, where we'll explore sensors, perception, and space-time awareness. The AEON-CASIMIR initiative continues to redefine what is possible in advanced vehicle design.